Alright, AP, let's finish up Chapter 3 with Sections 8 and 9, moving into Stoichiometry. Your objectives for Section 8: express the law of conservation of mass quantitatively and qualitatively using symbolic representations and particulate drawings. Use balanced chemical equations to generate mole ratios of different compounds in a reaction. Then determine through stoichiometric calculations quantities such as the number of moles or the mass of any reactant or product in a chemical reaction. Alright, let's get going. If we're trying to calculate masses of reactants or products in some sort of reaction, it doesn't matter if it's a reactant or a product. I'm just saying those are the two options that we have. The process is going to be the same. You're going to, number one, balance the equation for that reaction. Then convert the known mass, because the problem is going to have to give you some bit of information to start with. Now, if it's a mass, you start with the mass, you convert that mass into moles of that substance. Now, obviously, if the problem just gives you moles of that substance, you pick it up right here and use the balanced chemical equation to set up the appropriate mole ratios. You're going to use those mole ratios to calculate the number of moles of the desired reactant. So you're using those mole ratios as a conversion factor. That's going to allow you to go from talking about one substance to the other substance, meaning you'll be converting, talking about whatever substance the problem gave you to work with, and you need to start talking about the substance that the question is asking you about, what your answer is supposed to be talking about. Then lastly, if you need to, if the problem requires, convert from the moles of your desired substance into grams of the desired substance. That just depends on the question. So talking about stoichiometry, a stoichiometric factor or mole ratio is a conversion factor obtained from the stoichiometric coefficients in a chemical equation. Now I'm going, whoop, a little problem with technical difficulty with the microphone. Okay, all right. I'm going to use the term mole ratio. I'm not going to use the term stoichiometric factor. Some instructors do, some textbooks do, but for the most part, we're going to stick with mole ratio. But it's a conversion factor. Looking at this balanced equation that we have right here, we have three different relationships. Okay, we have the relationship between carbon monoxide and hydrogen gas. We have the relationship between carbon monoxide and then this hydrocarbon, this is CH3OH, and then the relationship between the hydrogen gas and the hydrocarbon, the CH3OH. We have three different relationships. The relationship between carbon monoxide and hydrogen is 1 mole to 2 moles. Now, the relationship is also 2 moles to 1 mole, going back the other way. And so that means from these three different relationships that we get, we can take these conversion factors and we can flip numerators for denominators depending on what substance we're going from and what substance we're going to. So realize out of each of these three relationships, you can get a total of 6 different conversion factors. So a little conceptual reference here. We have a certain amount of space. Now, how many cars can I park in that space? Well, that's going to depend on whether or not I'm using a 10-foot parking spot or a 25-foot parking spot, whether I'm parking nose in or if I'm parallel parking. If we're going to expand that into the atomic realm, 1 mole of carbon monoxide may be equivalent to 1 mole of CH3OH, or it might be equivalent to 1 mole of CO2 or to 2 moles of the CH3OH. It just depends on the reaction. So you have to look at whatever equation you're talking about in that specific problem. So an outline of how we use the mole ratio. Mole of substance A, again, that's whatever the problem gave you. Moles of substance B, that's what the question is asking about. And it's a simple conversion factor. Moles of what you want on top, moles of what you have on bottom. And you're going to go normal stoichiometric conversions before and after that point, because, again, you may need to do some sort of calculation, maybe a gram to mole calculation before, and then maybe a mole to gram calculation afterwards. You know, those are easy. But this is the new part that we're introducing here in Section 8. So let's put that into practice. When 0.105 moles of propane is burned in excess oxygen, how many moles of oxygen are consumed? So here's your balanced chemical equation. You don't even have to balance it. I did that for you because I'm so nice. What I'd like you to do here is use that mole ratio to convert from these moles of propane into moles of oxygen using the stoichiometric coefficients from this equation. Go ahead and press pause so you can try this on your own, because here comes the answer. 0.525 moles of O2 are going to be consumed when combusting 0.105 moles of propane. And so here's our big time outline. What we've already talked about so far in this presentation, the mole to mole ratio. And we're going to have a very simple stoichiometric scheme, and all we're doing is to this mole ratio conversion, we're adding a conversion factor from mass at the beginning, and then potentially a conversion factor back to mass at the end. Substances A and B, it does not matter where they are in the reaction. They can be two reactants, they can be two products, they can be one reactant, one product. It actually does not matter whatsoever. The reaction arrow does not really play a role in these stoichiometric conversions. Now the concept check, I'll give you the answer to this one. Please press pause so you can attempt this on your own. Consider the following reaction. If 6.25 grams of phosphorus is burned, meaning reacted with oxygen O2, what mass of oxygen does it combine with? Go and press pause, because here comes the answer. It's going to combine with 8.07 grams of O2. All right, here's some concept checks that I want you to try on your own. Press pause so you can work these out, but I will not give the answers during this PowerPoint presentation. If you want to check your answers, you're going to need to communicate with your classmates or with me through another avenue. Moving on to section 9, we are going to be carrying out calculations involving limiting reactants. So, objectives here. A few of the same learning objectives that you have already seen so far. Express the law of conservation of mass quantitatively and qualitatively using symbolic representations and particular drawings. Use stoichiometric calculations to predict the results of performing a reaction in the laboratory and or to analyze the deviations from the expected results. That's a new one. And then relate quantities, meaning the measured masses of substances, volumes of solutions, or volumes and pressures of gases, to identify stoichiometric relationships for a reaction, including situations involving limiting reactants and situations in which the reaction has not gone to completion. That's a new one. And these last two are also new ones. Determine the limiting reactant in a reaction. That's going to play into that third bullet there as well as the second bullet. And then calculate theoretical and percentage yields in reactions. Again, those two fold into the second and third bullets here. All right, so a limiting reactant. It's in the section title. So what is it? Many reactions are carried out with something that's called a limiting reactant. It's a limited amount of just one of the reactants, meaning you have plenty of the others, the other or others. The reactant that is completely consumed, okay, use all of it, but the reaction can't go any further because you ran out of one of the reactants. That is called the limiting reactant. Sometimes called the limiting reagent. That's the exact same thing. It's just your convention, your choice. I use the term limiting reactant. The limiting reactant is not necessarily present in the smallest amount. You might think, oh, whatever there's less of. Whatever there's less of, that's going to be the limiting reactant. That's not the case. It's what is consumed first. And so with that in mind, try to show you this idea. Let's look at this way that we can make meals, make lunches. Now, you make one sandwich, 2 cookies, and 1 orange, you got yourself a lunch. Fair enough, right? So which one is going to be the limiting reactant if we have 10 sandwiches, 18 cookies, and 12 oranges? Well, if whatever we have the least of, like, oh, we have 10 sandwiches, is that going to be the limiting reactant? No. When we go on to ask this question, how many of these packaged meals can we make, it's actually going to be the cookies. If we have 12 oranges, potentially we could make 12 lunches. If we have 10 sandwiches, we can potentially make 10 lunches. But with 18 cookies, we can only make 9 lunches. So in this example, this setup, this reaction, it's the number that has the most objects, 18 cookies. That is actually our limiting reactant because it's going to get used up before the sandwiches and the oranges.
Enter the sandwich shop. Click Sandwich Shop to enter. Complete sandwiches are made by combining one piece of meat with 2 slices of bread. Click the Make Sandwiches button. The sandwiches use all the meat, leaving excess bread. Now view the limiting reactant for NO2 molecules. Click the Limiting Reactant button. Product molecules are made by combining reactant molecules in the correct proportion. Click the React button. NO is the limiting reactant and is completely consumed. Excess oxygen remains after complete reaction.
All right, now here's that particulate view, the particulate representation of these stoichiometric calculations that we're referring to in the learning objectives. So if we have 28 grams or 1 mole of ethylene, and we react that with 128 grams, which is 0.8 moles, of bromine, we get 150 grams of 1,2-dibromoethane. Now that's a naming system that we're not going to go over in this course, so don't freak out. But also leftover ethylene. We ask the question, why is ethylene left over when we started with more bromine than ethylene? That's the question. Well, if we had more bromine, shouldn't we have leftover bromine? Here, we want to count the molecules. That's our hint. If we were actually going to do that, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules represented here with ethylene. 1, 2, 3, 4, 5, 6, 7, 8 molecules represented here with bromine. And so, yeah, if we're going to have a 1-to-1 reaction or something close to that, yeah, the bromine is actually going to get used up first, because remember, it's not grams reacting with grams here, it's molecules reacting with molecules. And so we have to be aware that we have more ethylene than we do bromine. Yes, the mass of bromine is greater, that's true, but the amount of bromine we have is actually less, and that's represented by the 0.80 moles of bromine as opposed to the full 1.0 mole of ethylene. So, when we're recognizing and trying to solve limiting reactants, we should recognize limiting reactant problems by the fact that amounts of 2 or more reactants are given. There's a problem in front of you, I give you, or the test gives you, or the AP exam gives you amounts of 2 or more reactants in the problem. That's one of the dead giveaways that you're talking about, some sort of limiting reactant problem. At least part of it will be a limiting reactant problem. One way to solve them is to perform a normal stoichiometric calculation of the amount of the product obtained, starting with each reactant. You're simply going to do 2 different conversions. Take the amount of one reactant, figure out how many of one of the products are generated, take the second reactant, again, stoichiometrically convert that to the amount of that same product generated. The reactant that produces the smallest amount of product is the limiting reactant. Now, that doesn't sound that complicated, but it does take a little bit of time because you're having to set up 2 separate conversions for the same problem. It ends up being pretty simple, though, so come in with a little bit of confidence because you can already do those types of things. Well, here is a concept check. Which of the following reaction mixtures would produce the greatest amount of product? Each involves the reaction symbolized by 2 H2s plus 1 O2 reacting to form 2 H2Os. If I have 2 moles of H2 and 2 moles of O2, 2 moles of H2 and 3 moles of O2, 2 moles of H2 and 1 mole of O2, 3 moles of H2 and 1 mole of O2. So, go ahead and press pause, generate your response, because here comes the answer. Well, here you go. Each produce the same amount of product. Each produce the same amount of product. Because what we're doing here, we have the first 3 potential responses, A, B, and C, all reacting to 2 moles. Okay, 2 moles with at least 1 mole of oxygen. So you're going to produce a certain amount of water. There's 2 moles of water. And with D, you're having 3 moles of hydrogen. So you might think maybe I'm going to make 3 moles of water, but we only have 1 mole of oxygen. With 1 mole of oxygen, we can only make 2 moles of water. So for each of these responses, A through D, we're actually always producing 2 moles of water. Now I want you to try this concept check. Press pause so that you can work this out. No answer here. Check with your classmates or myself through another avenue. Moving on to yields. There is a theoretical yield. A theoretical yield of a chemical reaction is the calculated quantity of the product in the reaction. When I say calculated, it hasn't happened yet. Okay, we haven't carried out the reaction and measured the product. We're simply calculating how much should be there. And I think, well, obviously it's going to be there. It's not, because we have something that's called an actual yield. Actual yield is the amount you actually get. Okay, actual yield will always be less than the theoretical yield, and actually for a lot of reasons. And this is a quick hint. If you ever get a theoretical yield that is smaller than your actual yield, or an actual yield that is larger than your theoretical yield, you know immediately that you've done something wrong. Something in your calculations is wrong. Go back and check that. But there can be many reasons. There are very large numbers of reasons why actual yield is always going to be less than theoretical yield. For example, there could be side reactions. Anything that happens reacts, in the atmosphere. They could also very easily react with oxygen that's in the atmosphere. It could very easily react with hydrogen that's in the atmosphere, or maybe nitrogen gases in the atmosphere, water in the atmosphere. And so these reactants that you're wanting to go into one specific reaction, they're actually participating in several different reactions, and so you're getting a mixture of products from different reactions, not just the one that you're looking at. Also, some reactions actually go in reverse of one another. They actually go back the other way, so that's another reason that you will get an actual yield that's smaller than the theoretical yield. Once you have your actual yield and your theoretical yield, it's actually very easy to state your percent yield. It's simply the percent of what you did get versus what you thought you'd get. You take your actual yield, divide it by the theoretical yield, and turn it into a percentage by multiplying by 100. Here's a real life example. Mixing solid zinc with solid sulfur. Yeah, you get a reaction, but instead of having just zinc sulfide as your product, you're going to get a whole bunch of zinc oxide, because there's going to be reactions with oxygen in the atmosphere. You're also going to get unreacted zinc, because not all of the sulfur potentially came into contact with zinc. Okay, it didn't have access to sulfur to react with, so you get unreacted zinc, and then you get impurities from the zinc and the sulfur itself. So again, many reasons why you get an actual yield less than theoretical. So hey, there's an animation problem there. Pretend that answer isn't there. I was going to give it to you anyway, so whatever. Ethyl acetate is a solvent used in fingernail polish remover. What mass of acetic acid is a CH3COOH, but what mass of acetic acid is needed to prepare 252 grams of ethyl acetate if the expected percent yield is 85.0%? Assume that the other reactant, ethanol, is present in excess, meaning you got plenty of that. That's not going to limit you at all. The equation for the reaction carried out in the presence of H2SO4 is the acetic acid plus the ethanol react to form ethyl acetate and H2O. Because we can calculate easily what the theoretical yield is, and we know that we want our percent yield to be 85.0%, we can plug those into this equation down here at the bottom, and we can calculate what our actual yield is going to be that we need. And so to get that actual yield, once we have that actual yield, we can carry out a normal stoichiometric calculation, convert that into the substance that we need, and that's going to give us the 202 grams of CH3COOH. All right, here is a concept check with no answer. I want you to try this on your own. You're going to have to check with your classmates or myself through some other avenue to check your answer. And lastly, Got a concept check. I'm not going to give you the answer to this one in this PowerPoint presentation. Please get together with your classmates or check with me through some other avenue. But this is a concept check for the whole chapter. The combustion of oxygen, of 1.5250 grams of an alkane-derived compound. Okay, alkane-derived compound. This is a hydrocarbon. Composed of carbon, hydrogen, and oxygen, yields 3.047 grams of CO2 and 1.247 grams of H2O. The molecular mass of this compound is 88.1 AMU. Draw the plausible structural formula for this compound. Is there more than one possibility? Explain this. Again, this is going to encapsulate everything that we've talked about in this chapter. This is going to be a tough one, so please make sure that you give yourself an opportunity to try this one out.